Welcome to The Explainer. I am genuinely thrilled you're tuning in today because we're about to take this incredible microscopic to macroscopic journey into something that literally dictates everything around us. We're talking about salts, the hidden engine of life and industry. We're going to explore how this one class of compounds controls everything from, the tint of the glass in your windows all the way to the actual beating of your heart. Now, I want to challenge you for a second. Is salt just a basic seasoning, or is it literally the engine of life? When you grab that shaker to put some of that white stuff on your fries, you probably aren't thinking about, say, immense electrostatic forces, or heavy industrial manufacturing, or the biological machinery keeping you alive. But today, we are going to completely change how you look at this everyday compound. The stakes here are massive, and we're about to uncover some seriously mind-blowing chemical foundations. Okay, let's dive into this. Here is the roadmap for today's explainer. 1. What exactly is salt? 2. 10 essential salt properties. 3. The rules of solubility. 4. The 8 types of salts. And 5. How salts power our world. Section 1. What exactly is salt? The scientific definition. To really wrap our heads around how salt shapes the world, we have to break down its fundamental building blocks. Basically, a salt is a crystalline, ionic compound, and it's born from a very specific, almost dramatic event, a neutralization reaction between an acid and a base. Picture this: a positively charged cation, usually a metal ion like sodium coming from a base, slams into a negatively charged anion like chloride from an acid. They crash together, they completely neutralize each other, and they form this perfectly balanced compound with absolutely zero net electrical charge. It is quite literally the perfect atomic marriage. Section 2. 10 essential salt properties. Physical and chemical traits. So, now that we know how they're born, let's look at how their physical traits totally dictate how they behave in the real world. Take their really high melting points. Everyday table salt, sodium chloride, needs a staggering 801 degrees Celsius just to melt. That's because of the sheer, fierce strength of its ionic bonds. But here's the crazy paradox. They're hard, sure, but they are incredibly brittle. A crystal can survive furnace-level heat, but if you just hit it, if you apply sudden physical pressure, the internal layers shift. Suddenly, like charges align, they violently repel each other, and the whole crystal just shatters instantly. And hey, not all salts are boring white crystals either. Transition metals create these vivid, popping colors. Copper sulfate is this brilliant, bright blue, and nickel sulfate is a deep green. Oh, and a lot of them are hygroscopic, meaning they actually suck water vapor right out of the air. Right. Moving over to their chemical properties, the absolute game changer here is electrical conductivity. In their solid state, salts are insulators. They don't conduct a thing, totally dead. But if you melt them down or just dissolve them in water, their ions suddenly become mobile. They instantly transform into powerful electrolytes that easily conduct electricity. They're also super reactive. If you drop an acid on a carbonate salt, it rapidly fizzes and releases carbon dioxide gas. They can completely alter the pH of water, making it acidic or alkaline. And, amazingly, they can actually trap whole water molecules right inside their crystal structure. We call those hydrated salts. Section 3. The rules of solubility. The microscopic tug-of-war. Have you ever wondered why some salts just instantly vanish when you stir them into water, while others sit at the bottom of the glass like tiny rocks? Well, it all comes down to an epic microscopic battle. On one side, you've got lattice energy. This is the salt fiercely fighting to hold its rigid crystal structure together. On the opposing side, you have hydration energy. That's the water molecules relentlessly attacking, trying to rip the salt apart. It's a completely binary outcome. If the water's hydration energy overpowers the bond, boom, the salt dissolves. If the lattice energy is stronger, it stubbornly stays a solid. Chemists have actually mapped this entire tug-of-war into a handy 8-rule system. On the soluble side, water literally always wins against nitrates, ammonium, and group 1 alkali metals like sodium and potassium. Always. Most chlorides and sulfates dissolve too, but, and this is a big but, there are strict exceptions. If chloride runs into silver, lead, or mercury, the salt wins the fight and stays insoluble. If sulfate meets barium, calcium, or lead, it's totally blocked from dissolving. Meanwhile, over on the insoluble side, most carbonates, phosphates, and hydroxides are fiercely stubborn. They actively repel water's attempts to break them apart, unless, of course, they happen to be paired with those super powerful group 1 metals we just talked about. Section 4. The 8 types of salts. Categorizing the compounds. Okay, Now that we've seen how they battle it out with water, we can actually categorize this massive chemical landscape. And what's super fascinating here is how everyday items in your house fit perfectly into these really rigid scientific categories. We're talking 8 distinct types. First, you've got normal salts, like table salt, which have no replaceable ions. But then you have acidic salts. Because they contain a replaceable hydrogen atom, we get baking soda. Then there are double salts, like alum, which actually lose their unique identity once they hit water. We've also got hydrated salts, the ones with chemically bonded water trapped inside. Epsom salt, the stuff you might toss into a warm bath, is a perfect example of that. And on the flip side, anhydrous salts have had every drop of water completely stripped away, making them incredibly powerful drying agents. Section 5. How salts power our world. Industrial, domestic, and biological uses. We've completely mastered the microscopic rules, so let's zoom all the way out into the macro world. Salts are literally the backbone of modern global industry. In metallurgy, they use a process called fluxing, where salts physically pull the impurities right out of molten metal. The massive chloralkali industry relies entirely on electrolyzing brine, which is just salt water, to produce the chlorine we need for PVC pipes, hydrogen for fuel, and caustic soda for paper and soap. If you're near a window right now, that glass only exists because a salt called soda ash was used to melt the silica. They even act as mordants, which basically lock the dye into the fabric of the clothes you're wearing today, so color doesn't just wash down the drain. But let's bring this complex chemistry right back to your kitchen. Why do we salt fish or make pickles? It's all about intense osmotic pressure. The salt literally sucks the water right out of bacteria, killing them on the spot and perfectly preserving the food. In a home water softener, sodium ions dynamically swap out with calcium ions to stop your plumbing from scaling up. It's a remarkably powerful abrasive for scrubbing down cast iron pans. And when you're cooking, salt is pulling double duty. It controls the growth of yeast in your bread, and it denatures the proteins in your meat to make it nice and tender. But honestly, the absolute most critical applications are happening right inside your body, right this second. Remember those mobile electrolytes we talked about earlier? Sodium and potassium salts literally drive the action potential in your nervous system. They form the biological electrical grid that lets your brain talk to your body. In hospitals, a 0.9% saline IV is what keeps a patient's blood volume stable. And remember how we said barium sulfate stubbornly refuses to dissolve in water? Well, doctors use that exact property to save lives. Patients swallow this dense, chalky barium sulfate, and because it won't dissolve, it simply coats their digestive tract and perfectly blocks X-rays, acting like a flashlight to illuminate their insides on a medical scan. So, what does this all mean? The crucial takeaway here is that absolutely everything comes back to salts. Think about this comparison for a second. Human life totally relies on hemoglobin to carry oxygen through our blood, right? Plant life relies on chlorophyll to drive photosynthesis. Both of these incredibly vital molecules are complex salts. The only major difference between them? Hemoglobin is a complex salt with a tiny iron ion sitting right at its center. Chlorophyll has a magnesium ion sitting at its center. That's it. The engine driving human life and the engine driving plant life are just very slight variations of complex salt structures. I mean, how incredible is that? Which brings us to our final thought for today's explainer. The next time you reach for that salt shaker to put a little dash on your dinner, I want you to pause. Look at those tiny white crystals and ask yourself, are you just seasoning your food, or are you literally holding the fundamental building blocks of industry, biology, and life itself? Thank you so much for exploring this with me today. Stay curious, and I will see you next time.